jump into the conduction band. That means 2 free electrons are available in the conduction band, 2 free holes available in the valence band. Okay, that's why density of electrons is equal to the density of holes. Now we will equal the two condition. We know, right? 2 into 2 pi me star kt to the power of 3 by 2. Here h square is there. Okay, exponential minus ec minus ef by kt. Okay, kt, and whole density is equal to 2 into 2 pi mh kt. So h square here whole power 3 by 2. Okay, exponential minus of ev ef minus ev by kt, right? Okay, this is whole electron density equal to the whole density. So here some of the terms will cancel out because 2 pi kt by h square. Here also 2 pi kt by h square is common, so we can cancel out the two terms. Okay, after cancelling whatever equal terms, what we will have here, me to the power of 3 by 2 exponential multiplying minus towards. Okay, then ef minus ec by kt, ef minus ec by kt, and ms to the power of 3 by 2, and exponential ev minus ef by kt, Okay, this we have remains after cancelling some of the equal terms or common terms. We have got this expression. Now from this expression, what we want? We want Fermi level. Okay, we are going to find out Fermi level in a intrinsic semiconductor. For that, what we have to do, just here is the ef is term is there, here is the ef term is there. We will bring one side and remaining term will send other side. Okay, then I am sending this me by 3h to right hand side. Okay, and this two second right hand side second term I am bringing to left hand side. Okay, now exponential. Okay, so here, so this is very simple calculation. Just you can easily do it. This one, exponential ef minus ec by kt. Okay, ec by kt. Here first term, second term, and here fourth term. I am bringing fourth term to left hand side. Okay, then here you can write this way, exponential ev minus ef by kt, and right hand side what we have, mh by me. Here both are having same power, so we can write 3 by 2. Okay, right. So e to the power of a and e to the power of b, what is the formula? E to the power of a and e to the power of, what is the formula here? How can we write this expression? What is the formula of e to the power of a by e to the power of b? If you listen the class, you will able to answer. If you are not listening classes, or just you are on somewhere else, you cannot listen. What is that?
E power a minus b.
Yeah, very good. Okay. Because this formula everybody knows, most of the know, but because nobody is listening, that is the thing. That's why you are what is going on class, you don't know. Once exam is coming, then you will not able to write. That time you will ask what are the important questions. This is very bad. Just learn the subject, whatever, whenever exams are there, whatever exams are there, doesn't care. Just you learn the concept, you learn the subject, then after that you try to go for exam. Okay, without concept, if you get 100 marks, also no use. Okay, so please attend class, please listen. Just you are, I don't know what should I say. Already I'm starting on what I'm telling you. Listen. Okay, that is the main thing. Okay, so we can write here e to the power of a minus b. Okay, I am writing minus is here minus ev, and this ef also comes to the here, it will become plus ev by here kt is there. Okay, just I am written e to the power of a minus b. Okay, e to the power of a minus b. Okay, mh by me to the 4 of 3 by 2 to the 4 of. Okay, now here we will simplify this expression. Please mute. Okay, further we will simplify this expression. Okay. ఏం కావాలయ్యా మీకు మ్యూట్ చేసి మాట్లాడండి ఒకవేళ మీ ఇంట్లో మాట్లాడదలుచుకుంటే. ఓకే, సో here 2EF is there, EF plus EF 2EF and minus of I am taking common EC plus EV by total KT is there. Okay, KT and here MH by ME to the 4 of 3 by 2 to the 4 of 3 by 2. Okay, from this expression just we'll apply logarithm to both sides. We'll apply logarithm to both sides. Then here exponential logarithm will cancel out. So 2EF minus EC plus EV by KT is equal to ln of MH by ME to the 4 of 3 by 2, right? So we'll further this, we will write this. Okay, so this expression we can write 3 by 2 also. 2EF is equal to, sorry, 1 minute please. Okay, 2EF is equal, we can, what we can write here, 2EF is equal, what we will write, EC plus EV by KT, EC plus EV by KT you can write here, you keep it like this way also, KT and plus what we can write here, 3 by 2, here 3 by 2 is there, ln of a power x is there suppose, or 1 by 2 suppose any constant, you can write out here ln of 1 by 2 ln of a, like this way you can write. Okay, ln of MH by ME. Okay, MH by ME. Okay, we'll further write EF, just EF is equal here this KT will cancel out, so this 2 also you come here. Okay, EC plus EV by 2 plus 3 by 4 KT here ln of MH by ME. Okay, MH by ME. This is the Fermi level in a intrinsic semiconductor. EF is equal to EC plus EV by 2. EV by 2 you can put a one bracket here for easy way. 3 by 4 KT ln of MH by ME. Okay, this is the Fermi level in a intrinsic semiconductor. If you write this expression within 2-3 steps we can complete it, but for understanding I am writing each step, that's why you feeling it expressions are very lengthy, but there is expressions are not lengthy, so very short only, but for explaining I am writing very step by step, that's why it is becoming a lengthy expression. So here Fermi level is EC plus EV by 2 plus 3 by 4 KT ln MH by ME. Okay, did you follow this one expression? Could you follow it with, could you follow this expression?
Yes, sir.
Yes, sir.
No, only what we have done, just very easy. We know carrier concentration of electrons or density of electrons and density of, from this expression we have rewritten this expression. EF is equal to, we taken out EF and remaining things we have written right hand side. That's it, nothing else. Okay, just we have in intrinsic semiconductor density of electrons is equal to the density of holes. That's it, very simple. Just you can write within 2, but I am written like this. Okay, this is the expression. Okay, now we'll see one more important thing here. Okay, if at 0 Kelvin, or what is this expression becomes, suppose we, if you want to write at 0, sorry, this expression, okay, or 0 Kelvin, or in case of MH is equal to ME, electron mass is, sorry, electron mass is, effective mass of electron is equal to the effective mass of electron. Okay, if you want to write T is equal to 0 Kelvin, effective mass of electron R is equal to the effective mass of hole. That time this term becomes 0. Second term becomes 0. That means what? F is equal EC plus EV by 2. EC plus EV by 2. So we are rewriting this expression in the case of 0 Kelvin, or in case of electron mass, effective mass of electron is equal to the effective mass of hole. So if you write that expression, this expression becoming a EC plus EV by 2. What does this mean? What is the meaning of this one? What does it mean? EC plus EV by 2 means what does it mean? What it will gives the information? What is mean by EC plus EV by 2 in words? What is
Ener-
meaning?
Energy of conduction and valency bond average.
Okay, that is means what? In a average we have taken average or average. Let's take average. If you say in your words only, average means EF is average of EC plus EV by 2, and average of EC and EV. That means what? So here this is the EV, right? Sorry, EC, lowest energy of conduction band. Okay, this is the EV, highest energy of valence band. Average of this one means where we can locate this EF exactly
Middle of
middle of the these bands. So here from this expression we can say the significance of this expression, or you can say the what information this expression gives means for intrinsic semiconductor at 0 Kelvin the Fermi level is exactly middle of the band gap. Exactly middle of the band gap. That expression means, so if you substitute the Fermi level equation easy that please mute. You are answering but unmuting without unmute you are talking with your family, something like that. Okay, so this EC plus EB by 2 means the Fermi level is exactly middle of the band gap, exactly middle of the band gap at 0 Kelvin, or in case of electron mass and hole mass, effective mass is equal. This is exactly middle of the semiconductor, middle of the band gap. That is the, that will give the this information. Okay, EC plus CVB is middle of the band gap. Okay, from this, and also here see here we will draw the how this Fermi level is changing. Okay, how the probability function, or you can say this one here. So mainly here one more thing, we will draw the Fermi level, how the electrons are occupying these states. Okay, suppose shall I take, we will take new page, then it is convenient. Okay, we will draw the how it is looks like. Okay, so this is the conduction band, you know, this is the valence band, you know. Okay, this is energy level, this is energy level, this is energies only. Bands means these are energy level. Okay, don't confuse. Okay, this is EC and this is EV. Okay, so at 0 Kelvin, if you draw the probability FFE, FFE will gives the information occupancy of energy levels, occupancy of electron in a energy level. If you draw this one, okay, at 0 Kelvin, this is completely filled. Okay, this is completely filled. Okay, this is 1. Okay, probability is equal to 1 at 0 Kelvin, because all electron, that means what? All electrons are occupied in the valence band only. There is no electrons available in the conduction band. There is no electrons available in the conduction band. Okay, if you increase this temperature, what happens if you increase this temperature? So some of the electrons will go into the conduction band here. Some of the electrons go into the conduction band electron. So how? So I am drawing here again a little bigger diagram. So this is EC and this is EV. Okay, this is EC. Okay, so this is energy levels. Here we are taking probability function. So at the, this is the Fermi level, let's take. Okay, at the, at 0 Kelvin only we are having all electrons are filled in the valence band only. There is no free electrons in the conduction band. if you increase temperature, what is happening? Some of the electrons are jumping from valence band to conduction band. Okay, in that case, you have to write, you have to draw like this. Okay, you have to draw this way, you have to draw it. Okay, you have to draw. Okay, this portion, and this portion is filled electrons here. Okay, that portion means what? Filled electrons. Here, this portion means what? Vacancy of electrons are holes, or you can say this much electrons leaves the valence band, and this much portion is filled in the conduction band. Okay, even if you increase further temperature, more number of electrons filled in this state, filled in the more number of case, more number of electrons are vacated in this region. Or if you increase temperature, more number of electrons, bound electrons, breaks the bond in the covalent in the valence band and jumps into the conduction band. So this is filling electrons. You can say this is filling. This area is increase the temperature. This area also increasing, and this area also increasing. That means what? More number of free electrons available in the conduction band. Here more number of free holes available in the valence band. Okay, if you see, carrier concentration is mainly proportional to the temperature, or you can take Fermi level also. EF is proportional to the temperature. So if you increase the temperature, the Fermi level shift near to the conduction band, or if it will shift towards the conduction band. That means more if you increase the temperature, very simple. Just we have a semiconductor at 0 Kelvin, all electrons, bound electrons, are filled in the valence band. There is no free electrons at 0 Kelvin. And the Fermi level also we are drawing middle of the band gap. So if you increase the temperature, whatever bound electrons in the valence band, they get some thermal energy, break the bond. After it is suddenly they conduction band by overcoming this band gap, jumping into the conduction band. Okay, like that, if you increase more temperature, more bound electrons break the bond in the valence band, and they will jump into the conduction band by crossing the band gap. Like that way, once the electrons leaves the valence band, that leaves a hole in the valence band. Okay, like that, once electrons jump the conduction, become a free in conduction band, and holes are free in the valence band. Like that, carrier concentration will be increased in a semiconductor by increasing the temperature. So more temperature means more number of free electrons available, more number of free holes available in a intrinsic semiconductor, so that we can increase the conductivity of semiconductor, intrinsic semiconductor. The intrinsic means pure semiconductor. For pure semiconductor, only way is increasing the temperature only. We can increase the current. There is no other option. If you increase the temperature, you will get the more current from the intrinsic semiconductor. That is the main reason for conductivity increase in the intrinsic semiconductor. Or you can say, if you draw the same levels, energy levels here, okay, this is the energy levels. Okay, so suppose here some of the electrons are occupied. Okay, that is, so density of states you can write this way, parabolic nature. Okay, density of states also you can draw like this way. This is EV and EC. So always this density of states are like a parabolic. Okay, so if this this one are holes, these are holes, and these are electrons. So this hole density always equal to the electron density in a intrinsic semiconductor. Okay, if somebody ask draw the density of states diagram for intrinsic semiconductor, just you have to draw. This is conduction band, this is EC, and this is EV, and this is the some energy scale, energy axis, or you can say energy axis. Density of states just like a parabolic. Density of states a parabolic. In the derivation also we have written Z of E is equal 4 pi by h cube and 2m to the 4 of 3 by 2 e to the power of half we have written, right? So density of state is proportional to the e power half. That means it is a parabolic equation, isn't it? It is a parabolic equation. Parabolic equation. So this is why we can draw a parabolic, and in intrinsic semiconductor you have to draw equal number of holes and equal number of electrons. Today just we have discussed these things. Carrier concentration is equal to the Ni square equal to N into P. From there we have derived expression for Ni. Just okay, I will write that Ni is equal to what is the Ni here? What is Ni? Okay, you have derived the expression for Ni. After that, N is equal to P. From there, we have derived expression for EF. From there, we have derived 0 Kelvin. Also, we have derived what is the EF, where it is lying. Okay, it is exactly lying between EC plus EV by 2. EC plus EV by 2. This is today we have discussed. Okay, so very simple. If you know concentration of electrons or concentration of holes or density of electrons and density of holes, you can solve the carrier concentration, and also you can solve the Fermi level. Okay, this is very important. They will ask derive the expression for Fermi intrinsic semiconductor, or they will ask derive the expression for density of holes or density of electrons in a intrinsic semiconductor. This way they will ask questions in the exam. So just practice this one. And one more important thing I want to tell you. Okay, today I will give some important questions for first unit. I will give important questions. Please write assignment and send to my mail. Okay, is it clear to everyone?
Yes, sir.